Okay, in this video I'm just going to discuss Euler's method again and then try to finish the example off where we had some difficulty before by doing an example by hand using Euler's method, and then I'll show how to implement in Maple in a separate video. Alright, so just to remember, alright, so what is Euler's method? Here's the vector form of Euler's method here. Alright, so to get the previous y, the next y value, we're going to take our previous y, add on delta t times f of the previous y. Now I just want to go over and just illustrate this graphically. What we're really doing is we're taking our initial starting point. In the picture I'm at 1, 3, I believe, and then we're going to, the idea behind Euler's method is to slide out a step of size delta t along the tangent line at the point, starting at the point where you're at. So each time we get a new approximate, we're going to use that new approximate point to get a new tangent line, slide out that new tangent line a step of size delta t. Alright, so this is very similar to what we saw for Euler's method for single variable equations. I'm just going to look at another one. This is from earlier in the semester. We went through this. Just one difference to notice in these graphs is we have t on the horizontal here, we have y on the horizontal here. You can explicitly see t, in this case, increasing by 1/2, which is the step size each time. Alright, that doesn't happen for systems. When we plot this in the phase plane, we don't explicitly see t in here. Alright, and that's okay. Delta t is still going to be in this, it's still going to be fixed for your problem, you know, a quarter or a tenth or whatever it might be. But notice that the gap in between these points is changing as we're going forward. Alright, and that's because the strength of the vector field is different at different points in the phase plane. Even though these arrows in Maple, they've all been scaled in the vector field to all have the same length. That's just for viewing purposes, right? The value of the vector field changes, and therefore the magnitude of the vector field is going to change as we go forward. Okay, so just a couple of notes to make before we go forward with this. All right, so I'm just going to go, I got a couple of still frames of that. Again, you can see in here that the size of the gap between these 2 points is different than the vector down below here in the gap between these 2 points. But really what's happening in Euler's method is you're starting at wherever you are. And again, I froze it in this point. That's our previous y value. So that's the vector. We want to think about this geometrically. That's the vector y sub k minus 1. And what we're going to do is we're going to add on a certain amount. We're going to go slide out the tangent line to any solution at that point a certain amount. So let's come back to that in just a minute here, what we mean by that. Alright, so I'm going to scroll back up to explain that step. So to get the next approximate, what we want to do is take our previous point, our previous vector, start there, and we want to add on a step of size delta t in the direction of the tangent line. Well, from what we've learned before, the derivative vector at the corresponding value for t is a vector which is tangent to the graph. And therefore what we really want to do is multiply the derivative vector by delta t. But the system tells us what the derivative vector is equal to. It's equal to the vector field f of y at the right hand side. So really, to get the next approximate, we're going to take our previous approximate, add on delta t times f of y of t sub k minus 1, which is our previous y value. Alright, so that right there, that observation is really important there. What are we adding on? We're scaling the derivative vector, but via the differential equation, the derivative vector is equal to the output of the right-hand side. So thinking about this in this picture right here, what is this vector we're adding on to it? This vector we're adding on is delta t times the vector field at that point. Alright, so that's the vector we're adding on. So the vector field's actually probably long, the value of the vector for f is probably longer than is drawn here, but it's scaled down by a factor of delta t. So that's where we're seeing the strength of the vector field depending on where we're at. Delta t is going to be fixed in each step. Okay, so that's the idea behind Euler's method. Now just keep, also one other thing for us to keep in mind when we're doing this by hand or even in Maple or in Excel, is that the right-hand side vector field, we're usually thinking about that, the first component of that being f, the second component of that being g. So we can write this in vector form that has a nice geometrical viewpoint. To do this schematically, we might want to look at this in component form, right, and separate this out into your first component and your second component. So to get the next x, we take the previous x component plus delta t times little f, and little f is the right-hand side of the first differential equation, all right, for our system. All right, and to get the next y, we're going to take the previous y plus delta t times g, which is the right-hand side of the second equation in our system, right? So our system, when we think about them in component form, is going to be dx dt equals little f of xy, and dy dt is going to be little g, right? Mostly we're going to be encountering autonomous systems here in this unit, right? So that's what we'll do next. So let's implement that in an example, and this is from the exam 2 review that we've seen posted, and it's the last example that I have on here. So let's work through this example together. We'll verify our work in using Microsoft Excel, and then in a different video I'll show you how to implement this in Maple. Alright, so for this problem we're using Euler's method with a step size of 0.25. Now in here this is telling us our initial t value is 0, and if our step size is 0.25 and we're supposed to get out to time 1 and we're starting at 0, we're going to go to a quarter, a half, 3/4, and then get to 1, right? And I've got those t values listed in the chart there. The initial condition is 2,5. That means x is 2 and y is 5 when t is equal 0. All right, so let's start to implement Euler's method here. Now keep in mind here, this is my function little f, this is my function little g, right? So little f is 2x plus 3y, right? That's the right-hand side of the first differential equation. Little g is the right-hand side expression for the second differential equation. Okay, so let's go down below here and let's compute some of these next x values and y values. So what's the next x and the next y going to be? It's going to be the previous x, which is x of 0, plus delta t, and in our case we assumed delta t, or we were told delta t was 0.25, times f of the previous x and previous y. Well, that's going to be 2 times x of 0 plus 3 times y sub 0. And again, where is this coming from? This is coming from the right-hand side of equation 1 in our system, 2x plus 3y. The next y value is going to be the previous y plus 0.25 times the value of the right-hand side of the second equation, which is negative x plus y, so it's going to be negative x sub 0 plus y sub 0. Now, it's just a matter of us plugging these numbers in. All right, what is x sub 0? It's 2. Y sub 0 is 5, so it's going to be 2 plus 0.25 times 2 times 2 plus 3 times 5. All right, if you compute that all out using a calculator, you're going to get 6.75. So that's our next x approximate. For the y, our previous y was 5, so it's going to be 5 plus 0.25, our step size, and then negative 2 plus 5. So we negate our previous x plus our previous y. If you compute that all out, you're going to get 5.75. All right, so take a calculator and compute that. You're not going to do that by hand. All right, so 6.75 and 5.75. All right, I think let's do one more step. We'll double check this in Microsoft Excel, and that'll be it for this video. All right, so now we're just going to rinse and repeat, but now we've got our new x and new y as 6.75 and 5.75. All right, so to get x2, what are we going to do there? We're going to take our previous x, x1, plus our step size, 0.25, times 2 times our previous x, plus our 3 times our previous y. And let's just plug those numbers in right away. What was our previous x? Our previous x was 6.75. Put that here and here. Our previous y value was 5.75. All right, and we're going to put those in, and then just crunch the numbers. All right, if you work this all out, it's going to come out to 14.4375. All right, the next y value, what will we do there? Our previous y, which is 5.75, plus delta t, which is 0.25, and then it's minus our previous x plus our previous y. So now we got to plug those values in, and we had 6.75 and 5.75 respectively. And if we work all of this out, crunch the numbers there, we're going to get 5.5. All right, so that's the next step using Euler's method. Okay, so when we get up here, 14.435 and 5.5, and then we would reiterate that 2 more times, doing the same exact set of very similar sets of steps here with our new x and our new y value. All right, now let's just implement that using Microsoft Excel just to check our work. So I think you can see how to finish it from here. All right, and then there's a question on the exam where I'm asking you to do it by hand. So show me the work there. Okay, so let's implement that in Excel here quick. Let me show you how to do that to check it. So in here I've got the t values, I've got our initial x and our initial y. What we're going to do is go into the next x position and put our formula in. So we have to start with an equal sign. Our previous x is in cell B2, so it's going to be B2 plus delta t, which is 0.25, times the right-hand side of the x equation says 2 times our previous x, which is in B2, plus 3 times our previous y, which is in cell C2. All right, so do that, press enter to execute it. Yep, we're getting 6.75. All right, now similar for y, we're going to go equals, and then just do what Euler's method tells us to do. So it's our previous y value, which is in cell C2, plus our step size, 0.25, times the right-hand side of the y equation says to negate your previous x plus your previous y. All right, so negative B2 plus C2, and we press enter. All right, now to make Excel implement that, highlight both of those, go to the lower right corner until you get the black cross sign, and then left click and drag that down, and then that's going to repeat the calculation. And we see the next one verifies what we had done, 14.4375 and 5.5 for y. And you can check the other 2 values, all right, by hand and verify that that's matching up what we would see here in Excel. All right, so that's how to implement Euler's method by hand and using Microsoft Excel. We'll do this also in Maple in a different video.